Welcome to this comprehensive module on orchestration in DevOps. Throughout this session, we'll explore how orchestration has revolutionized the way we handle containerized applications and microservices architectures. By the end of this module, you'll have a thorough understanding of container orchestration platforms, with a particular focus on Kubernetes, the industry-leading solution. Whether you're new to DevOps or looking to enhance your existing knowledge, this course will provide you with both theoretical foundations and practical insights that you can apply in real-world scenarios. Let's begin by understanding what orchestration means in the context of DevOps. In today's complex software environments, applications are increasingly built using containers, lightweight, portable units that package everything needed to run a piece of software. However, as your application grows, you might find yourself managing dozens, hundreds, or even thousands of these containers across multiple servers. This is where orchestration becomes essential. Think of orchestration like conducting an orchestra. Just as a conductor coordinates multiple musicians to create harmony, container orchestration coordinates multiple containers to ensure your application runs smoothly. It's the automated process of managing, deploying, scaling, and networking these containers in a distributed environment. When working with modern microservices architectures, you'll often find yourself dealing with multiple containers that need to communicate with each other, scale based on demand, and maintain high availability. Manual management of these containers would be not only time-consuming but also error-prone. Orchestration automates these tasks, making your applications more reliable and easier to manage. The history of container orchestration is fascinating and closely tied to the evolution of modern DevOps practices. While containers themselves have been around for decades, with technologies like root jails dating back to the 1970s, container orchestration as we know it today gained significant momentum with the rise of Docker in 2013. Docker revolutionized the way we think about application deployment by making containers more accessible and easier to use. The ability to package an application with all its dependencies into a lightweight, portable container was groundbreaking. However, as organizations began adopting Docker containers at scale, they quickly realized they needed a way to manage these containers effectively. This need led to the development of various orchestration solutions, but the real game changer came in 2014, when Google introduced Kubernetes. Kubernetes, often abbreviated as K8s, was built on Google's decade-plus experience running containers at scale with their internal system called Borg. By open-sourcing Kubernetes, Google shared their expertise in container management with the wider technology community. It's worth noting that the history of container orchestration is still being written. As new challenges emerge in cloud-native computing, orchestration platforms continue to evolve to meet these challenges. Understanding the need for container orchestration is crucial for any DevOps professional. As organizations increasingly adopt microservices architecture, the complexity of managing applications grows exponentially. Let me explain why orchestration has become indispensable in modern software deployment. Imagine you're running a large e-commerce platform with dozens of microservices, user authentication, product catalog, shopping cart, payment processing, and more. Each service runs in its own container, and you need multiple instances of each service to handle user load. Without orchestration, you'd need to manually deploy each container instance, ensure containers are running on appropriate servers, monitor container health, replace failed containers, scale services up or down based on demand, manage network connections between containers, handle storage requirements, coordinate updates and rollbacks. This manual management becomes virtually impossible as your application grows. In some organizations, teams spend more time managing containers than developing new features. This is where container orchestration becomes essential. One particularly illustrative case I encountered was with a media streaming service. They started with a few containers running their core services, but as they grew to millions of users, they ended up managing thousands of containers. The turning point came when they experienced a major outage because they couldn't scale their services quickly enough during a viral event. After implementing proper orchestration, they could automatically scale from hundreds to thousands of containers within minutes, ensuring service reliability even during unexpected traffic spikes. Container orchestration provides automation for all these tasks, making it possible to automatically deploy containers based on defined specifications, monitor container health, and automatically replace failed instances, scale services up or down based on defined metrics, manage networking between containers automatically, handle storage attachments and persistence, coordinate rolling updates with zero downtime. This automation not only makes management possible at scale, but also reduces human error, improves reliability, and frees up DevOps teams to focus on more strategic tasks. Let's dive deep into the compelling benefits that container orchestration brings to modern software deployment and management. These advantages have made orchestration an essential part of DevOps practices. First, let's talk about scalability. In today's digital landscape, the ability to scale applications quickly and efficiently is crucial. Orchestration platforms provide automatic scaling capabilities that can adjust your application's resources based on actual demand. For instance, during Black Friday sales, an e-commerce platform might need to handle 10 times its normal traffic. Orchestration systems can automatically spawn new container instances to handle this increased load and scale them back down when the traffic subsides. High availability is another critical benefit. Orchestration platforms continuously monitor the health of your containers and automatically recover from failures. If a container crashes or a node fails, the system automatically restarts the container or redistributes workloads to healthy nodes. This self-healing capability ensures your applications remain available even in the face of hardware or software failures. Resource optimization is particularly important from a business perspective. Orchestration platforms can efficiently pack containers onto your infrastructure, maximizing resource utilization while ensuring each container has the resources it needs. This optimization can lead to significant cost savings, especially in cloud environments where you pay for resource usage. Load balancing in orchestration systems ensures that traffic is distributed evenly across your container instances. This not only improves application performance, but also prevents any single instance from becoming overwhelmed. The load balancing is intelligent and can take into account factors like container health, current load, and resource availability. Finally, automated deployment capabilities streamline your continuous integration and deployment (CI/CD) pipelines. You can define your desired application state declaratively, and the orchestration system will automatically make the necessary changes to achieve and maintain that state. This automation reduces deployment errors, enables faster releases, and makes rollbacks simpler if issues are detected. While container orchestration offers numerous benefits, it's important to understand its potential drawbacks and challenges. Being aware of these limitations helps you make informed decisions and prepare for the challenges you might face. The first and most significant drawback is complexity. Orchestration platforms, particularly Kubernetes, have a steep learning curve. The complexity comes from the numerous concepts, components, and configurations you need to understand. For instance, in Kubernetes, you need to grasp concepts like pods, services, deployments, stateful sets, ingress, and more. This complexity can be overwhelming for teams new to container orchestration. Resource overhead is another consideration. Orchestration platforms themselves require computational resources to run. For example, a basic Kubernetes cluster needs multiple control plane components and worker nodes, each consuming CPU, memory, and storage resources. In smaller deployments, this overhead might be significant relative to the resources used by your actual applications. Vendor lock-in can become a concern, particularly with cloud provider-specific orchestration services. While platforms like Kubernetes are open source and portable, using managed services like Amazon EKS or Google GKE might tie you to specific cloud providers. The integration with cloud-specific services and tools can make it challenging to move to a different provider or bring workloads on premises. Security concerns also need careful consideration. Orchestration platforms centralize control over your applications, which means a breach in the orchestration layer could potentially affect all your workloads. Additionally, the complex nature of these platforms can make it challenging to implement and maintain proper security controls. Some successful organizations acknowledge these drawbacks and plan accordingly. They invest in training, carefully consider resource requirements, plan for portability, and implement robust security measures from the start. It's also worth noting that for smaller applications or simpler deployments, the complexity of full orchestration might not be justified, and simpler solutions might be more appropriate. Let's explore the major players in the container orchestration landscape. Understanding the strengths and focus areas of each platform will help you make informed decisions for your specific use case. Kubernetes, often called K8s, stands as the clear leader in container orchestration. Developed by Google and now maintained by the Cloud Native Computing Foundation, it has become the de facto standard for container orchestration. Its rich feature set, extensive ecosystem, and strong community support make it suitable for complex, large-scale deployments. However, its power comes with complexity, and it might be overkill for simpler use cases. Docker Swarm, integrated into the Docker ecosystem, offers a simpler alternative to Kubernetes. It's particularly appealing if you're already using Docker and need basic orchestration capabilities. While it may lack some of Kubernetes' advanced features, its simplicity makes it an excellent choice for smaller deployments or teams just starting with container orchestration. Amazon ECS, Elastic Container Service, and EKS, Elastic Kubernetes Service, cater to AWS users. ECS is Amazon's proprietary orchestration service, deeply integrated with other AWS services. EKS, on the other hand, is Amazon's managed Kubernetes service. Both options are well suited for organizations heavily invested in the AWS ecosystem. Microsoft's Azure Kubernetes Service, AKS, provides a managed Kubernetes environment for Azure users. It offers seamless integration with Azure's security, monitoring, and management tools. Google Kubernetes Engine, GKE, is Google's managed Kubernetes service. Given that Google originally developed Kubernetes, GKE often leads in implementing new Kubernetes features. It's particularly strong in areas like autoscaling and cluster management. Apache Mesos, while less focused specifically on containers, offers a broader distributed systems framework. It can manage various workload types beyond containers, making it suitable for organizations with diverse computational needs. The choice of orchestration platform often depends on factors like existing infrastructure and cloud provider relationships, team expertise and learning curve considerations, scale and complexity of applications, specific feature requirements, budget constraints, integration needs with other tools and services. Now let's begin our deep dive into Kubernetes, the most widely adopted container orchestration platform in the industry. This section serves as an introduction to what makes Kubernetes special and why it has become such a crucial tool in modern DevOps practices. Kubernetes represents a paradigm shift in how we manage containerized applications. Originally developed by Google, based on their experience running massive-scale systems, it was open-sourced in 2014. The name Kubernetes comes from Greek, meaning helmsman or pilot, which perfectly describes its role in steering and managing containerized applications. What makes Kubernetes particularly powerful is its declarative approach to application management. Rather than telling Kubernetes exactly how to run your applications, you declare the desired state, what you want your application to look like, and Kubernetes continuously works to maintain that state. This approach significantly reduces operational complexity and human error. Think of Kubernetes as an intelligent system that's constantly working to match the current state of your applications with your desired state. If a container fails, Kubernetes automatically restarts it. If a node dies, Kubernetes reschedules the affected containers to healthy nodes. If traffic increases, Kubernetes can automatically scale your application to handle the load. The true power of Kubernetes lies not just in its technical capabilities, but in how it transforms operational practices. It enables teams to deploy applications consistently across different environments, scale applications automatically based on demand, update applications without downtime, recover automatically from failures, optimize resource usage across their infrastructure. In this course, we'll explore these capabilities in detail, starting with basic concepts and moving to advanced features and real-world usage patterns. Let's explore the fascinating evolution of Kubernetes and its remarkable journey to becoming the industry standard for container orchestration. This history helps us understand both its capabilities and its design philosophy. Kubernetes' story begins inside Google, where it evolved from an internal system called Borg. For over a decade, Google used Borg to manage their massive container workloads, running billions of containers per week. This experience proved invaluable in designing Kubernetes, as it incorporated many lessons learned from operating at such scale. When Google open-sourced Kubernetes in 2014, it was a landmark moment in the DevOps world. The decision to make it open source was strategic. Google recognized that for Kubernetes to succeed, it needed to become a community project rather than a single vendor solution. This decision proved crucial for its adoption and evolution. The formation of the Cloud Native Computing Foundation, CNCF, in 2015 marked another significant milestone. By donating Kubernetes to the CNCF, Google ensured its development would be vendor-neutral and community-driven. This move attracted contributions from major technology companies and individual developers worldwide. The adoption timeline tells an impressive story. 2014, initial release. 2015, adoption by early innovators. 2016, production use by major companies. 2017, widespread enterprise adoption begins. 2018 to 2019, becomes the de facto standard. 2020 present, focus on security, ease of use, and edge computing. Today, Kubernetes is used by organizations of all sizes, from startups to enterprises, and runs some of the world's largest and sophisticated deployments. Let's explore the key features that make Kubernetes such a powerful container orchestration platform. These features form the foundation of its capabilities and demonstrate why it has become the industry standard for container orchestration. Container orchestration is at the core of Kubernetes. It automates the deployment, scaling, and management of containerized applications. This means you can define how your application should run, and Kubernetes handles the details of making that happen across your infrastructure. Scaling is one of Kubernetes' most powerful features. It supports both manual and automatic horizontal scaling of applications. Through the horizontal pod autoscaler, Kubernetes can automatically adjust the number of running containers based on CPU utilization, memory usage, or custom metrics. The self-healing capability of Kubernetes is particularly impressive. If a container fails, Kubernetes automatically restarts it. If a node dies, Kubernetes reschedules all the containers running on it to other healthy nodes. If a container doesn't respond to health checks, Kubernetes replaces it. This self-healing mechanism ensures high availability of applications with minimal human intervention. Service discovery and load balancing are built into Kubernetes. It assigns unique IP addresses to containers and DNS names to services, enabling seamless communication between different parts of your application. The integrated load balancer distributes traffic across multiple instances of your application, ensuring optimal resource utilization and high availability. Rolling updates and rollbacks are crucial for maintaining application availability during updates. Kubernetes can update applications progressively while monitoring health, automatically rolling back if issues are detected. This feature has transformed how organizations handle application updates, virtually eliminating deployment-related downtime. Configuration management through config maps and secrets provides a clean separation of application code from configuration. This allows you to modify application settings without rebuilding containers, making it easier to manage applications across different environments. These features work together to create a robust platform that can handle complex deployment scenarios while simplifying operational tasks for DevOps teams. Understanding how Kubernetes differs from other orchestration platforms is crucial for making informed decisions about your infrastructure. Let's examine these distinguishing features in detail, particularly comparing Kubernetes with Docker Swarm and Apache Mesos. When comparing Kubernetes with Docker Swarm, several key differences emerge. Kubernetes boasts a larger, more active community, which translates into more resources, tools, and third-party integrations. This extensive ecosystem means you're likely to find solutions for specific challenges and benefit from continuous improvements. However, this comes with increased complexity. Teams may initially struggle with Kubernetes' learning curve, while Docker Swarm's simpler architecture allows for quicker adoption in smaller deployments. Docker Swarm's integration with Docker makes it an attractive choice for teams already familiar with Docker. It uses the same command line interface and doesn't require learning new concepts. However, this simplicity can become a limitation for more complex scenarios. The comparison between Kubernetes and Apache Mesos reveals different architectural philosophies. While Kubernetes is specifically designed for container orchestration, Mesos is a more general-purpose distributed systems kernel. Mesos can manage various types of workloads beyond containers, including big data frameworks like Hadoop and Spark. Mesos' flexibility comes with its own trade-offs. Its broader focus means it might require more setup and configuration for pure container workloads compared to Kubernetes. However, for organizations running diverse workloads, Mesos' ability to handle different types of applications can be advantageous. In practice, these differences often guide platform selection based on specific needs. For container-specific orchestration with robust features, Kubernetes. For simpler deployments with Docker integration, Docker Swarm. For diverse workload types beyond containers, Apache Mesos. The choice between these platforms should align with your organization's needs, team expertise, and growth plans. Before diving into Kubernetes implementation, it's crucial to understand the key considerations that will impact your success with the platform. Let's examine these important factors that should influence your decision-making process. Complexity is perhaps the most significant consideration when adopting Kubernetes. The learning curve is steep, and your team will need to understand various concepts like pods, services, deployments, stateful sets, and more. Some organizations underestimate this complexity, leading to delayed projects and frustrated teams. Success requires a commitment to training and gradual adoption. Manage this complexity by starting with a small, non-critical application, investing in comprehensive team training, partnering with experienced Kubernetes consultants, implementing the platform in phases, developing clear operational procedures. Resource overhead is another crucial consideration. Kubernetes requires significant computational resources for its control plane and worker nodes. A production-grade cluster typically needs multiple master nodes for high availability, adequate CPU and memory for system components, storage for etcd and other system data, network bandwidth for internode communication. Use case evaluation is essential. While Kubernetes is powerful, it might not be the best choice for every scenario. Small applications with simple deployment needs might be better served by lighter weight solutions. I've advised several startups to start with simpler orchestration tools and migrate to Kubernetes only when their complexity demands it. Cloud vendor lock-in considerations are particularly relevant when using managed Kubernetes services. While Kubernetes itself is cloud agnostic, managed services often integrate deeply with provider-specific features. This can make it challenging to move between cloud providers or to on-premises deployments. Real-world impact of these considerations. Operational complexity affects team productivity and deployment speed. Resource overhead influences infrastructure costs. Use case alignment determines long-term success. Vendor lock-in impacts future flexibility. Understanding these considerations helps you make informed decisions about Kubernetes adoption and implementation strategy. Welcome to our exploration of Kubernetes architecture. Understanding this architecture is fundamental for anyone working with Kubernetes, as it provides the foundation for all operations and troubleshooting. The architecture of Kubernetes follows a master worker pattern, comprised of various components that work together to maintain the desired state of your cluster. Let me break this down. At the heart of Kubernetes is the control plane, often called the master node. Think of it as the brain of your Kubernetes cluster. It consists of several critical components. The API server is the front end for the Kubernetes control plane. All communication between components and external users goes through the API server. The scheduler handles the intelligent placement of workloads. It watches for newly created pods with no assigned node and selects a node for them to run on. This decision-making process considers various factors like resource requirements, hardware/software constraints, affinity/anti-affinity rules, data locality. The controller manager runs controller processes that regulate the state of the cluster. These controllers are like thermostats for your cluster, continuously working to maintain the desired state. For example, the replica set controller ensures the right number of pod replicas are running. etcd is the cluster's database, storing all cluster data in a consistent and highly available manner. Some organizations learn the hard way about the importance of properly backing up etcd. It's crucial for disaster recovery. Worker nodes are where your applications actually run. Each worker node runs several key components. Kubelet is the primary node agent. It ensures containers are running in a pod. I often explain Kubelet as the worker node supervisor. It takes orders from the control plane and ensures they're carried out. The container runtime, like Docker or Containered, does the actual work of running containers. While Docker is commonly used, there's a trend toward using Containered directly for better performance and simplicity. Understanding this architecture is crucial for troubleshooting cluster issues, planning for high availability, implementing security measures, optimizing cluster performance. Teams that invest time in understanding this architecture are much more successful in their Kubernetes journey. Let's dive into the fundamental concepts that form the building blocks of Kubernetes. Understanding these concepts is crucial for effectively working with the platform. Nodes are the worker machines in Kubernetes, either physical or virtual, where your containerized applications run. Each node contains the services necessary to run pods and is managed by the control plane. Proper node management is crucial for cluster stability. Some organizations successfully implement node pools with different capabilities, like GPU-enabled nodes, to optimize resource allocation. Pods are the smallest deployable units in Kubernetes. Think of a pod as a logical host for one or more containers that share network and storage resources. They're designed to run together and scale as a unit. Services provide a stable networking abstraction for accessing pods. They solve the critical problem of discovering and connecting to pods that may be created, destroyed, or moved around. Replica sets ensure that a specified number of pod replicas are running at all times. They're the engine behind Kubernetes' self-healing capabilities. Deployments provide declarative updates for pods and replica sets. They manage rolling updates and rollbacks, making it possible to update applications with zero downtime. Key practical implications. Nodes focus on capacity planning and maintenance strategies. Pods designed for appropriate container grouping. Services plan your network architecture. Replica sets configure for high availability. Deployments implement robust update strategies. These concepts work together to create a robust platform for running containerized applications at scale. Let's explore the key components that make up the Kubernetes system. Understanding these components is crucial for operating and troubleshooting Kubernetes clusters effectively. The control plane serves as the brain of Kubernetes, managing the overall state of the cluster. A properly configured control plane is crucial for cluster stability. Let's break down its components. The API server is the front door to the Kubernetes control plane. All communication, whether from users, nodes, or internal components, must go through the API server. The scheduler is responsible for placing pods on appropriate nodes. It makes these decisions based on various factors. Resource requirements, hardware/software constraints, affinity/anti-affinity rules, quality of service, COS, requirements. The controller manager runs various controllers that regulate the state of the system. Each controller is a control loop that watches the state of the cluster and makes changes to move the current state towards the desired state. For example, node controller monitors node health. Replication controller maintains the correct number of pods. Endpoints controller populates the endpoints object. Service account and token controllers create default accounts and API access tokens. etcd is a distributed key value store that acts as Kubernetes backing store for all cluster data. Proper etcd backup and maintenance procedures are crucial. I've helped organizations implement robust backup strategies after they learned this lesson the hard way. The kubelet runs on each node and ensures that containers are running in a pod. It's like a node-level supervisor that takes instructions from the control plane. Common tasks include starting and stopping containers, performing health checks, reporting node and pod status, handling container lifecycle events. The container runtime is responsible for running containers. While Docker is commonly used, Containerd is gaining popularity for its simplicity and performance. When helping organizations choose a container runtime, I emphasize considering factors like team expertise, tool compatibility, performance requirements, security considerations. Understanding these components helps with troubleshooting cluster issues, planning for high availability, implementing security measures, optimizing cluster performance. As you work with Kubernetes, you'll interact with these components regularly, either directly or indirectly. Let's examine the key processes that drive Kubernetes operations. Understanding these processes is crucial for effectively managing and troubleshooting your Kubernetes clusters. Pod scheduling is a sophisticated process that determines where pods should run in your cluster. The scheduler considers multiple factors when making placement decisions. Resource requirements and availability, node selector and affinity rules, anti-affinity constraints, taints and tolerations, quality of service, COS class. Cluster networking is a complex but essential process that enables communication between pods across different nodes. Kubernetes sets up a virtual network where each pod gets its own IP address. Pods can communicate directly with other pods. Services provide stable networking endpoints. Network policies control traffic flow. Understanding this process is crucial. Self-healing is one of Kubernetes' most powerful features. The platform continuously monitors the state of pods and containers. Nodes, storage volumes, network endpoints. When issues are detected, Kubernetes automatically takes corrective action. Restarting failed containers. Replacing unhealthy pods. Rescheduling pods from failed nodes. Reattaching storage when possible. Scaling processes in Kubernetes can be both manual and automatic. The horizontal pod autoscaler, HPA, automatically adjusts the number of pods based on observed metrics such as CPU utilization, memory usage, custom metrics, external metrics. Understanding these processes helps you design more resilient applications, troubleshoot issues effectively, optimize resource usage, implement proper monitoring and alerting. These processes work together to create a self-managing platform that can run applications reliably at scale. Let's explore the detailed architecture of Kubernetes, focusing on how its components interact to create a robust container orchestration platform. The control plane components maintain the desired state of your cluster. Understanding these interactions is crucial for effective cluster management. The API server acts as the gateway for all cluster interactions. It validates and processes REST requests, updates etcd with cluster state changes, serves as the single source of truth for the cluster. The scheduler watches for newly created pods with no assigned node and selects an appropriate node for them to run on. This involves resource requirements evaluation, constraint checking, affinity/anti-affinity rules application, priority considerations. The controller manager runs controllers that regulate the cluster's state. Each controller is a control loop watching the shared state through the API server. Seed stores all cluster data in a consistent and highly available manner. Proper etcd management is crucial for cluster health. Users interact with the cluster through kubectl, the command line interface, Kubernetes dashboard, the web-based UI, custom applications using the Kubernetes API. The control plane communicates with worker nodes through the kubelay, which ensures containers are running in pods, mounts volumes to pod specifications, performs health checks, reports node and pod status, handles pod lifecycle events, manages container runtime, downloads pod secrets, enforces resource limits. The kubelet on each node registers the node with the cluster, monitors pod specifications, ensures containers are running and healthy, reports back to the control plane, executes probe checks. Each node runs a container runtime that's responsible for pulling container images, starting and stopping containers, managing container lifecycle, handling networking and storage. The networking layer implements pod-to-pod communication, service discovery and load balancing, network policy enforcement, ingress traffic management. Storage management is handled through persistent volumes for storage resources, persistent volume claims for requests, storage classes for dynamic provisioning, volume plugins for different backends. Understanding these components helps you design resilient applications, implement monitoring strategies, troubleshoot issues, plan for scaling. Minikube creates a single-node Kubernetes cluster running in a virtual machine on your local computer. This local setup is invaluable for learning Kubernetes concepts, developing applications, testing deployments, experimenting with configurations. The beauty of Minikube lies in its ability to replicate most Kubernetes features in a lightweight environment. While it's not suitable for production workloads, it provides nearly all the functionality you need for development and testing, including pod deployment and management, service creation and discovery, config map and secret handling, persistent volume management, ingress controller support. A particularly effective use case is for a DevOps team that uses Minikube to validate Kubernetes manifests before production deployment, test application behavior in a Kubernetes environment, develop and test operators and custom controllers, train new team members in Kubernetes concepts. As we proceed through this section, you'll learn how to install and configure Minikube, work with basic Kubernetes objects, deploy applications locally, test your configurations, debug common issues. Remember, Minikube is your stepping stone to mastering Kubernetes in larger production environments. Let's explore the compelling benefits that make Minikube an essential tool for Kubernetes development and learning. Local Kubernetes testing is perhaps the most immediate benefit. Minikube provides a fully functional Kubernetes environment on your laptop, allowing you to test deployments before pushing to production, validate Kubernetes manifests, experiment with new features, debug applications in a Kubernetes context. The isolated environment that Minikube provides is invaluable for learning without affecting production systems, testing potentially risky configurations, experimenting with new Kubernetes features, developing and testing applications safely. Learning Kubernetes becomes much more practical with Minikube. Its local nature allows you to understand core concepts through hands-on practice, experiment with different configurations, learn kubectl commands safely, explore Kubernetes APIs without risk. The easy setup process is particularly beneficial for teams new to Kubernetes. Minikube's simple installation and startup process helps overcome the initial hurdles of learning container orchestration. Teams can focus on learning Kubernetes concepts rather than struggling with complex cluster setup procedures. Real-world benefits I've observed include faster development cycles, reduced production issues, more confident deployments, better understanding of Kubernetes concepts, improved team collaboration. These benefits make Minikube an essential tool in any DevOps professional's toolkit. Let's walk through the process of installing Minikube on your local system. This installation process is crucial for getting started with your local Kubernetes development environment. The first step is installing a hypervisor. Minikube supports several options: VirtualBox, cross-platform and free; KVM, popular on Linux systems; HyperKit, designed for macOS Hyper-V, native to Windows. I've helped numerous teams with Minikube installation, and I always emphasize choosing the right hypervisor based on your operating system and requirements. The installation process varies by operating system. On macOS, using Homebrew Package Manager. On Windows, using Chocolatey or Direct Download. On Linux, using package managers or direct download. Common installation challenges I've encountered include virtualization not enabled in BIOS, insufficient system resources, network connectivity issues, hypervisor conflicts. To ensure a successful installation, verify system requirements. Enable virtualization in BIOS if needed. Close other resource-intensive applications. Ensure adequate disk space. Remember, proper installation is crucial for a smooth Minikube experience. Take time to verify each step before proceeding. Understanding how to properly start and stop Minikube is essential for managing your local Kubernetes environment effectively. To start Minikube, you use the minikube start command. This command creates a virtual machine, installs Kubernetes components, configures the kubectl context, sets up the container runtime. I recommend additional start options: minus memory, specify RAM allocation, minus -minuscpus. Set number of CPU cores minus -disk size. Define VM disk size minus -driver. Specify hypervisor. The Minikube stop command gracefully stops your cluster. Saves cluster state. Shuts down the VM. Preserves all configurations. Maintains deployed resources. Best practices I've developed include regular cluster stops to free resources, checking cluster status before operations, maintaining cleanup procedures, documenting custom configurations. Understanding these commands helps you manage system resources effectively, maintain stable development environments, troubleshoot startup issues, optimize local development workflow. Let's discuss the proper procedures for uninstalling Minikube, which is important for maintaining a clean development environment or when troubleshooting installation issues. The uninstallation process begins with the Minikube delete command, which stops the running cluster, removes the virtual machine, cleans up configuration files, releases allocated resources. I recommend these additional cleanup steps. Remove Minikube binary. Clean up ~.minikube directory. Remove kubectl context entries. Delete associated Docker images. Here is a comprehensive cleanup procedure. Stop all running services. Minikube stop. Verify no lingering processes. 2. Delete the cluster. Minikube delete -minusol. Remove all profiles and cached images. 3. Clean up system files. Remove configuration directories. Delete cached credentials. Clean Docker image cache. Or remove the binary. Use Package Manager or manual removal. Verify complete removal. Best practices for uninstallation. Backup important configurations. Document custom settings. Verify resource release. Check for leftover files. This thorough approach ensures a clean slate for future installations. Let's explore the fundamental Kubernetes objects you can work with in Minikube. Understanding these objects is crucial for developing and testing your applications locally. Pods are the basic building blocks in Kubernetes. In Minikube, you can deploy single and multi-container pods, test pod communication, experiment with pod lifecycle, practice pod management. Here is a simple example. Services in Minikube allow you to expose applications internally/externally, test service discovery, practice load balancing, understand network policies. Deployments provide rolling updates capability, rollback functionality, scale management, application lifecycle control. Config maps and secrets let you manage application configuration, store sensitive information, test configuration changes, practice security patterns. Working with these objects in Minikube helps you understand Kubernetes concepts, test deployment strategies, debug application issues, develop best practices. Let's explore kubectl, the command line interface for interacting with Kubernetes clusters, including your Minikube cluster. Understanding kubectl is essential for anyone working with Kubernetes. The kubectl create command allows you to create new resources, deploy applications, set up configurations, initialize services. Start with simple create commands as shown here. The kubectl get command is your window into the cluster. List resources. Check status. View configurations. Monitor deployments. Try common get commands shown here. The kubectl apply command is crucial for updating resources, implementing changes, managing configurations, rolling updates. The kubectl describe command provides detailed information. resource specifications, event history, status details, configuration data. The kubectl delete command helps you remove resources, clean up environments, reset configurations, manage cluster state, mastering kubectl commands, improves troubleshooting efficiency, speeds up development, enhances cluster management, facilitates automation. We've covered a lot of ground in this module on container orchestration, with a particular focus on Kubernetes and Minikube. This is a good time to pause and reflect on what we've learned. Throughout this module, we've explored the fundamentals of container orchestration, the evolution and importance of Kubernetes, key components and architecture of Kubernetes, practical implementation using Minikube, essential kubectl commands and operations. I encourage you to take this opportunity to ask questions about any topics we've covered. Questions often lead to valuable discussions that enhance everyone's understanding. Whether you're curious about technical details of Kubernetes architecture, best practices for container orchestration, real-world implementation challenges, career paths in DevOps, industry trends and future developments. Let's address some of the common questions that often arise when working with Kubernetes and container orchestration. These topics often benefit from further discussion. Scaling strategies in production environments, security best practices for container orchestration, integration with existing CI/CD pipelines, migration strategies from other orchestration platforms, performance optimization techniques. I encourage you to continue experimenting with Minikube, join the Kubernetes community, participate in local DevOps meetups, share your learning experiences, build practical projects to reinforce your knowledge. Remember that mastering container orchestration takes time and practice. The concepts we've covered provide a strong foundation, but real expertise comes from hands-on experience and continuous learning. Please feel free to reach out through the course platform for any additional questions or clarifications.